Good morning, good afternoon, good evening, wherever you are, and welcome to the latest edition of FreeThought Hour. Now, before we launch into tonight's show, well, it is tonight here, but I know may not be where you are. If only the world was flat. But before we do launch into tonight's show, I just want to promote last week's show because we had a fantastic conversation with ethicist Blay Whitby. And I have been in communication with him since because our Prime Minister here in the UK lost his ethics advisor. It's the second one that he's lost in about 18 months. They keep resigning because they think they're being ignored. So I had a little chat with Blay via email and asked him whether he thought it was ethical for the next person to apply for this vacancy. Anyway, I can share that with you maybe later on in the details under this video. But tonight, Tercia, who do we have tonight?
We are rocking tonight. We have Dr. Wendy Rocks tonight.
Yes, you do.
She's a geologist. So we are rocking. We are either going to circle the globe or flatten it out. But however we're going to do it, it's going to be a rocking good show.
Should we bring her in?
I think so, yes.
Wendy, how the devil are you?
I'm doing well. How are you?
Good. Yes,
Good.
we're all okay here. Thank you. Yes. So I love your handle, Dr. Wendy Rocks. But
Thank you.
your real
I
name
didn't
is
come up with it, so
No? Oh, okay.
I used to be just my first initial and last name, and then that was sort of boring. And so I put out a social media call on Twitter and said, "Hey, I'm looking for a new handle. What do you all think?" Yeah. And I picked my top 4 favorites and put them out as a poll on Twitter, and people voted, and I was kind of glad they picked the one they did because I like it a lot.
Yeah, it's great. Absolutely. So whereabouts are you? You're on the East Coast somewhere, aren't you?
Yeah, right outside of Washington, D.C.
Mm-hmm. And you're working for a non-profit?
Yes. We are funded by the National Science Foundation. And so the name of the nonprofit is IRIS, or the Incorporated Research Institutions for Seismology. And we manage and maintain a huge suite of seismic instruments and geodetic instruments for use by the scientific community, as well as the Global Seismographic Network in collaboration with the U.S. Geological Survey. So that's about 150 seismic instruments that are operating around the world at all times. And all of our data is freely accessible and available to anyone.
Wow. That sounds like such a virtuous job to be doing to me.
Open source data is important. So
yes, absolutely. But there's something else that you're renowned for, isn't there? Because you're the mother of twins.
I am the mother of twins. I actually have three kids, a 17-year-old daughter and 7-year-old twin boys. So yeah, it's a lot.
Okay.
It's good, but it's busy.
Do they like rocks?
They do like rocks. So the first year of the pandemic, I homeschooled the little guys. You know, the older one was able to be online and handle her own stuff. But one of the things that we did was kind of incorporate rocks into all different lessons. And so, for instance, one of our online friends on Twitter has written a book about the minerals and gems of every state. And so we had a big map of the United States, and they have these giant, as you might expect, bags of rocks and minerals that we've collected and that they've gotten through the years. And so they went through and had to figure out each state and then find its mineral and then put its mineral on the state. So it was geography and science all at once.
Mm.
Well, you'll enjoy this story. My youngest brother, he's the age gap between me and him is bigger than between you and your kids and the older one, but he's a geography teacher in Abu Dhabi, and in 2013 the two of us went to visit our brother in the UK, and I think it was the first case of visitors, just tourists. We actually left some things because we brought rocks back from we brought some rocks from Dover, the White Cliffs, and must I say that? Can I go to jail for that? I don't know. But we had to repack and unpack our luggage because we had rocks in our bags, and everywhere we went, we picked up rocks and stones. So we literally came back with bags of rocks because, rocks are lovely. Rocks
aren't they wonderful? And see, rocks are they're not just interesting to look at. And they don't just sort of bring you back to the memories of the place where you collected them. If you can learn how to read the rocks, you can read the whole history of the earth. And so, going to school to kind of learn to speak the language of the earth was really interesting. It's like being a geologic detective, being able to look at the rocks and read the story.
Absolutely. I want to ask you a bit about that, because the geologic record, what do you call it? The scale of all the different strata. That's something that I've argued about with a certain Kent Hovind. You may have heard of him. He's a young Earth creationist who has a dinosaur museum.
Yes. Okay. Yeah.
And he thinks that there's no such thing as the strata, the what's the name for it? The whole record, the geological timescale.
Yeah.
He thinks it's because you can only see bits of it. There's nowhere that the whole thing. He wants a great big hole so that he can see all the layers in one view.
Well, there's lots of different ways that we can date rocks. There's two main ways, and one is that looking at how the rocks are positioned in relation to each other. So if you imagine coming home from work, you grab your mail and you throw it on the counter. You don't want to deal with it. And the next day you grab your mail, you throw it on the counter. By Friday, you have a big stack of mail. What should you look at first? The bills on the bottom, because those are the oldest. Rocks are the same way. The rocks that are on the bottom are going to be the oldest. The rocks near the top are going to be the youngest because of the way they get laid down. And so there's the relationship of rocks that we can learn about. There's fossil assemblages that you can get age information out of. And then one of the things that I actually do is date rocks using the minerals that are inside the rocks. And so you can use lots of different mineral systems to do that. The ones people are most familiar with is usually carbon-14. And that's for things that we want to date that are relatively recent in time. We can use these very cool tiny minerals called zircons in order to date rocks back millions and even billions of years. And so we have lots of different lines of evidence that tell us how old rocks are. And we don't necessarily need all of the rocks in one complete sequence in order to understand how the history of a place has changed through time. So people can argue about whether or not one line of evidence or another line of evidence may be flawed. But when you take all of the different lines of evidence together, it's a very compelling story that the rocks are actually, millions and billions of years old in some cases.
Yeah, absolutely. And when you have an outcrop like a cliff or a canyon wall, you can see sort of a chapter in the book, and the chapters are in sequence as you explain. So you don't have to see the whole book at once. You can just see bits of it, but then fit them together because you know where they overlap.
Right. And the fossil assemblages, that was one of the first ways people started to piece the story together. They would see fossil A and fossil B in this one rock. And in the rock above it, A would have disappeared. And they would now see rock B and rock C. And then above that, they would see C, D, and E. And then they could start to connect different places. And a lot of this happened in England. They could connect different places across the map and say, aha, these rocks have the same distinct fossil assemblage. Therefore, I think that maybe they were deposited at the same time, even though they're in different places. And so then even if you're missing the stuff on the top, if it's been eroded away, you can say, but the stuff over here still has more of that record. There's additional chapters that I can read. And I know now that these go together. Yes.
Only last weekend I was in Devon, which of course have got a whole period named after it, the Devonian.
Yep.
And also near here, there's the Dorset coast, which is, what's that called? It's a dinosaur. No, it's not the dinosaur coast. The Isle of Wight is the best site in Europe for dinosaurs. And they've just discovered the biggest one, which is even bigger than T-Rex.
What?
Yeah.
That's where Mary Anning operated, am I right?
I believe so.
Are you thinking of she sells seashells on the seashore?
That's it. Yes,
Yes.
yes.
That
yes.
was in Dorset. Yeah, that
Yes.
was it Weymouth or might have been another, because we have a lot of little coastal towns along there. It could have been Weymouth or another one. Swanage, it might have been. I can't remember. But yes, that's where that comes from. So you're right. This is where it was mostly started, the whole idea of geology. Yeah.
So Wendy, I'm no geologist, but my brother being in love with rocks and geology and geography, something that I've come to learn in reading books like Bill Bryson's A Very Short History of Nearly Everything, and being exposed to my brother exposing me to rocks and all these books. The thing about geology that strikes me is that you can go very small and you can go into the chemistry of rocks, and that gives you a whole lot of information. And then you can zoom out and you can go and look at the layers and the strata, and that gives you a picture. And then you can use the very small on the chemical and the microchemical scope, and you put that together and you have this whole picture of not only the structure of the planet that we live on, but also the life on this planet. And it without saying a single word, we get so much information by this thing. There's a whole idea of zooming in and then zooming out and then getting this picture, because we don't think about this planet that we walk on. It feels so solid, but it's moving and changing all the time as we speak, and it shapes our lives. It shapes everything about us, and we don't even think about it because we're so small. We're such a little blink in time on this planet. It's just, to me, that's something about geology that boggles. It breaks my brain a little bit.
Well, to add another dimension to that, we can go down to the geochemical signatures of rocks and learn more about them. We can zoom out and look at continents and understand how huge rock formations fit together. And so we call that the spatial scale that we're looking at. We also think about the temporal scale. So we're looking at processes that are happening. If you think of an earthquake, that's over seconds or minutes. And then we also are looking at the course of geologic time. So earthquakes, which is what I study, the actual earthquake itself is a very short blip, shorter, far shorter than our human lives. And it's just a brief moment in time. And yet multiple earthquakes that accrue through time are what create our huge mountain ranges like the Himalayas. So we have both this spatial scale that we can look at the rocks and the geology on, and we have this temporal scale. So may add another break to the brain.
Add another brick in the wall. I have a question, and I don't. It's probably a stupid question, but do you think we'll ever be able to predict earthquakes in any accurate way, or is it just going to be? Is there any way of predicting it as we stand now?
I would never say never, but I don't think that we're close. We understand a lot about how the Earth works, and the Earth is a huge and complex system. As it stands right now, we don't know what is the straw that breaks the camel's back, so to say, when we're talking about what's going to cause an earthquake to begin. So we know that stress is building up through time, mainly because of the motion of the tectonic plates. We know about where that stress is accumulating, and we know about how much stress faults can take. Now that gets us into the realm of 30, 40, 50 years, plus or minus, right? But
doesn't
that's
help
not
much.
what people want. People want to know that it's going to happen at 3 o'clock on Tuesday. And so the other problem is that we don't know when the earthquake is going to stop. So the magnitude of an earthquake is dependent in part upon the length of the fault that breaks during the earthquake.
Right.
And so nobody cares about the little earthquakes. We have hundreds and hundreds and hundreds of those every day.
Yes. I was in one a long time ago. I was asleep in my lodgings in Portsmouth and, as a student, and we were woken up because our bed shook, and that was it.
Yeah, people don't want to know about that. If you got an alert for every earthquake that happened just in the state of California every day, it would be 14, 15 alerts a day. Most of those are so small that people don't feel them. So people only want to know about the big earthquakes. But when an earthquake starts, one of the questions people are asking, is there something inherent in the first few seconds of the fault breaking that tells us whether it's going to break the whole entire fault or whether it's going to stop it?
Okay.
So is it going to be a big earthquake? Is it inherently a big earthquake, or is it a small earthquake? Now, some faults are small. They're not going to produce large earthquakes, but for the ones that can, what makes it start? What makes it stop? Why exactly does it start at that moment? So what we do instead is something called earthquake forecasting, which is rather like a weather forecast, only a much larger time scale. So instead of saying, there's a 60% chance of rain on Wednesday at 9 o'clock, we'll say, there's an 87% chance of an earthquake of magnitude 6.7 or greater in the Bay Area in the next 30 years.
Yeah, that's not very helpful if you want to avoid it.
Well, that's another thing. Do we really want to predict the earthquake, or do we want to learn how to live with the earthquakes, build safer structures, make sure that our population knows what to do, those sorts of things?
Yeah.
When I was in San Francisco one time, we were in a square somewhere, and then this enormous stentorian voice shouted out, it was a practice for what might happen, if there is an earthquake, shouted out some warning about, I don't know, get out of the buildings or something. And that must be a regular thing over there.
There are earthquake drills. They're very important. So research from social scientists, Sarah McBride and others, has shown that if people don't get that muscle memory, they're less likely to do the right thing and more likely to panic or do the recommended practice. Another important thing is they look to see what other people are doing. Peer pressure, no matter how old you get, still a thing. So you only need one or two people to drop, cover, and hold on. In the United States, that's the recommended practice during an earthquake. And if two people do it, then the rest of the people will do it. So the idea is if we can practice over and over again, we can get a population of people that knows what to do, or at least a subset that will lead the others to the right choice.
Yes.
So if where I live is actually close to Cape Town, and in the 50s there was a massive earthquake in a town, Tolbach, that's about 60 kilometers away. I think a number of people. It was the biggest earthquake in South Africa. So the area that we live in, that I live in, is the most earthquake prone, because fortunately South Africa is not a place very prone to earthquakes. But I'm going to remember. So is it drop, cover? The safety precaution?
Drop down, take cover underneath a sturdy object, and then hold on either to the table or whatever's over top of you, or hold on to your head and neck.
Okay, drop, cover, and hold on. I'm going to remember that, because that's a. I was wondering, the main purpose of the organization that you work for, is it to sort of to be able to look forward, or is it or back, or a little bit of both, and with an eye towards managing, like you say, it doesn't seem we're going to predict it, but knowing where earthquake prone areas are, and teaching people what to do and how to prepare, and what to expect after a massive earthquake.
Well, we're only 50 people. We couldn't do nearly all of that. So we have a much smaller section of the pie. We are the ones that provide the instrumentation and provide the seismic data for the scientific community. So we facilitate the science, and people can use it to do all of those things you just mentioned. Another thing that the science that we do facilitates is verification of the Comprehensive Nuclear Test Ban Treaty. So we can tell the difference between earthquakes and bombs, for instance.
That's very useful.
That was one of the reasons seismic networks were originally set up in the 50s, was to monitor nuclear explosions, and they still serve that purpose.
And they're still reporting on North Korea, where they're continuing to explode bombs.
Well, when that happens, we can see it. And North Korea is an interesting place, because they're, one of the test detonations that they did was actually very close to the location of an earthquake that was a similar size to the bomb that they detonated. So it's a wonderful teaching opportunity to say, look, this is what a bomb explosion looks like, and this is what an earthquake in the same general area looks like, recorded on the same seismic instrument. So people can say, oh, look, yes, that does look different. I don't know what that wiggle means, but I can see that those things are not the same.
Yes, yes.
That's quite important. I mean, can you imagine if you have some crazy person who thinks an earthquake is an atomic bomb, and he presses the button and it was just for an earthquake?
It happens. It happens a lot, especially because many places that are experiencing political unrest and are having issues with all sorts of different things are also prone to earthquakes. And so often there will be a larger earthquake followed by aftershocks, which are smaller earthquakes, and people will think there's a conspiracy. There's actually bombs being detonated. There's some attack along the border of this or that country. And we can say, no, 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 these are earthquakes. This is what a bomb looks like. This is what an earthquake looks like. This is not what that is.
And you know, I never thought about, sorry, John, I interrupted you, but it just goes to show, you know, we think we talk about science and we're talking about rocks and earth and geology and geography, but here is something that science is doing that can have such a massive impact in something totally non-related, just because science enables us to give the correct information about the correct thing at the right time, and it can prevent further catastrophes, even if you can't predict earthquakes. Wow, that's so interesting. Amazing.
So there's lots of things that we use it for. And then there's just the things that are, I don't know, I call them the wonder and discovery things. So for instance, you may know that NASA put a seismic instrument on Mars. It was the InSight mission, and it was called SEIS, the seismometer. And it was to detect earthquakes, marsquakes, as they're called, and other impacts. And the idea is that they wanted to look at the structure of the Martian planet. They wanted to see what was inside Mars, in the same way we use earthquakes to look at what's inside Earth. We also manage and house all of that data. So if you want to look at the Mars data or the moon seismic data, we have all of that too. So it's a great opportunity for educators to look at all kinds of data and see the things we can do. And it's a great way for just like the public to explore and discover, because this is the data. This is what the NASA scientists look at. This is what the seismologists are looking at. And here, you can look at it too. We'll provide you some tools and some explanations, but here it is.
That's right. That's the great thing about science, because it's available to everyone. You don't have to be told and believe the person. You can actually handle the goods yourself. But I wanted to bring you the bad news, because it was recently reported that although the InSight seismometer on Mars has discovered that the crust is a bit thicker than Earth, and yes, the core is liquid like on Earth, and so it did or does have a magnetic field. The bad news is that the solar panels have got covered with Mars dust, and it's going to have to pack up soon.
It's always sad when that happens.
Okay.
I feel bad for all of those rovers and landers that get left behind, and they get anthropomorphized in those cartoons, and I'm like, oh, they're so sad, they're all alone. But it did a wonderful service. We learned some really amazing things. It lasted longer, than what was expected. So I think it was an incredibly successful mission, and people are going to be studying what came out of that for years and years to come. So
one day when we land on Mars, we'll send a man with a feather duster to wake it up again.
I've seen them.
At least a medal or something. Good job. A little pat on its little head.
Yes.
Wendy, do you know any geologists who are young Earth believers?
No.
Are there such people who just? I suppose. No. Okay.
Because I know many geologists that are spiritual or religious. I know none that are young Earthers.
No.
Okay.
No. That would be some brain discrepancy of some sort, wouldn't it? To try and hold those. What is it? Different orders. No, I'm trying to think of the phrase that was given to holding two different ideas in your head at the same time. Noma. It's noma, isn't it?
Non-overlapping magisteria.
That's it.
Non-overlapping magisteria. Yeah.
Yes. Thank you. Yes. Well done.
Because in South Africa, there's a big following of Kent Hovind and Ken Ham and those guys. And in fact, I spoke to somebody he's a professor in law, but he's highly educated. and he's a young Earth creationist, and he told me that he doesn't accept any of the evidence of an old Earth. And the question I want to ask you, Wendy, is if somebody tells me that, and I'm not a geologist, and they say none of the dating methods are accurate or reliable, what's the one thing that I can say, except for what I tell them? If you're a geologist, what would you say to convince a professor who's but he's convinced that the Earth is young? Is there something? What would it take? What do I tell such a person?
The hard thing about this conversation, and I grew up Southern Baptist, and I have people in my family that are young earthers.
Okay.
It takes a lot of evidence I've found given to people spaced over a long period of time. It's never just one piece of evidence, because one piece of evidence is not always convincing.
Yeah.
And at some point, they're not going to be convinced because they hold a world paradigm that's just different. So like, if we could just, in science, there's this idea that if we give people enough facts and information, then they'll come to the same conclusions that we came to with our logical way that we think. But people don't actually make decisions based on their values, based on facts. They make decisions based on values and belief systems, primarily religion and political affiliation. And once you start to undermine those two things in any way, make them question the premise of those, it causes the cognitive dissonance that people really try very hard to avoid. And so you have to give people little bits of information over long periods of time, and they have to be delivered by a trusted source. They have to be delivered respectfully. They have to be delivered in a way that the people are able to receive it. And so I don't think that there's any one thing that we can point people at to say, this is the smoking gun, because there is no smoking gun. We came to this because of lots of different forms of evidence from lots of different sources over decades and decades and decades. So it's a body of knowledge that leads us to this. And maybe you can poke holes in one thing, but you can't in all of them. And so
I've come to the conclusion after many years of being a teacher, a science teacher, that people, first of all, people don't like being told in general. Secondly, there's the only person that can persuade somebody is them. They have to come to their own
seed. You can plant the seed, and maybe it will sprout, but we're not usually around to see that part.
No.
True. So convincing young Earth creationists is a bit like predicting earthquakes. You need a long time span, and you're probably not going to get it right, but just keep going at it gently, slowly. It's like erosion, just like water flowing over rocks to smooth them out.
I also think it's really key for us to understand why they hold the belief that they do. Because if we don't understand why they hold that belief, we don't understand where the misconception lies. They believe that for a reason. And that reason to them is very valid. We may not value it, but it is valid and valuable to them. And so by understanding their perspective, that can give us an idea of how to proceed and address kind of the root cause of their thinking. And it's, in the end, I think it's about having a conversation rather than, like you said, John, telling somebody what the facts are, what's right, what's correct.
Well, I'm going to modify what I said now, because I've decided that up to about the age of, I don't know when, 7, people will accept being told. But then the door comes down, and after then, they want to find out. So, I experienced this as a science teacher in secondary school, where we wanted the children to do the experiments and come to their own conclusions, and that way they understood and believed, rather than standing up the front and lecturing, which doesn't make the same impression.
I also think, and I've heard some educators talk about different ways to approach pedagogy around contentious issues like evolution. where you don't actually ever say the contentious word. You just present the evidence and lead them through the sequence. And then at the end, once they have followed the logic, you say, and that's evolution. And they've already understood without having the pushback that comes just from the contentiousness of the topic that they've absorbed from other things.
Yes. Show them the evidence, let them form their own conclusion. So I wanted to talk to you because I know that you don't just do earthquakes, do you? You do what did you call it? A fast-acting geologic incident or event. So what does that include? Does that include volcanoes, pyroclastic flows?
So my actual science, I study earthquakes. You know, I study ancient earthquakes. I date landforms that tell us about earthquakes. But in my, 25 years in this profession, I've done mainly a lot of communication. And when you're talking about, I call them rapid onset geologic hazards. So things like earthquakes, volcanic eruptions, landslides, tsunamis, the communication principles are very similar in that you have to communicate the risk and the hazard before it happens, because once it starts, you don't have time to get to people in the same way. And so there's a different strategy talking about those sorts of things than there are about things like, say, hurricanes or snowstorms or other types of natural hazards that people experience. And so I think a lot about how to communicate with people in the sunshine days, before anything happens, in those instances where it's occurring, and then in the aftermath. And there's a lot of messaging that goes into those three different, spaces of time.
What about those movies where everybody's driving up the hill and the city's crumbling? They're no help, are they?
No, I mean, I love The Rock, Dwayne Johnson. Like, I love him. He's awesome. But if he could stop doing movies like San Andreas, that would be real helpful to the rest of us. Because people sort of get that in their head, and it develops a real sense of anxiety because they are events that don't happen very often, and they can be incredibly damaging and destructive. And they're scary enough without the cinematography that goes along with it. So But the cities are not necessarily going to be crumbling. LA is not going to rip in half. The tidal wave doesn't actually sweep over the tops of buildings in this huge breaking wave. But things actually do fall down. Buildings can collapse if they're not properly built. Bridges can sustain damage. Tsunamis really do come and sweep through cities and cause devastation. So they are real hazards. They're just not quite as cinematic.
No.
So do you do any, sorry, John, I wanted to ask Wendy if she does. Do you do any field work? Do you ever go out and do you visit the sites and look at the instruments and
well, I used to primarily do field work and lab work. So I worked quite a bit in Bolivia and Argentina. I've worked a lot on the San Andreas Fault. I spent a lot of time in the Himalayas in Ladakh, India, working on a fault system there that's very similar to the San Andreas fault system. And we would go out for months at a time and collect field data, collect rocks, do geologic mapping, dig down inside the fault to look for evidence of ancient earthquakes, and collect rock and dirt samples to take back to the lab to date when those earthquakes happened. And then I had my twins. And then it was a pandemic. And so there's not been a lot of field work in the last years. But I did recently go to Guatemala to visit my friend who's doing her PhD in volcanoes, volcano sociology. So she's studying people that live around active volcanoes.
Around volcanoes.
And we did do some very serious research, but it was more about the best margarita in Antigua than it was about the volcanoes.
Well, that's important too. I mean, can
that's
save
all the
lives.
Research, right?
Absolutely.
You blog about your twins, don't you? Tell us a bit about that.
Yeah. So my husband and I struggled to get pregnant. And that was really hard because I am the kind of person where I set my mind to something and I generally try and make it happen. I mean, it's not like I was 35 saying, I'm going to get a gold medal in the Olympics and gymnastics, but reasonable things. So when I couldn't get pregnant, it was very distressing. And, we wanted a family. We ended up doing infertility treatment, which was very isolating for me as a graduate student, because everybody else is trying desperately not to get pregnant. And I really wanted to get pregnant. And so I found the internet to be this real source of solace and camaraderie, sharing stories with other people going through the same thing. And so when I had my twins, I started a blog called Twinning at Motherhood that was about some of those same challenges. Raising twins is different than raising one child. And I didn't know anybody that had kids, or especially that had twins. And so it allowed me to build a community. That's one of the things I feel like I want to do in the spaces I'm in. I want to build community. So it gave me an outlet to write about things. It allowed me to kind of form a community with other mothers of multiples. And so, yeah, it was a lot of fun. I don't post on there as much now because I'm busy doing other things, but I do try and put something up once a month or so.
How old are they?
They're 7 now.
Yeah. We have a 7-year-old in this house too. Yes.
It's a lot of energy.
Yes, absolutely. So
do they share your interest in rocks? Do they
Yeah.
do they ever, I mean, you haven't gone on field trips recently, but do they know what you do? Do you tell them?
Oh yeah. Oh, they, it's funny. I was just talking about this with my mom because, most kids don't know what their parents do, but my kids know exactly what I do because I talk about it on TV and I'm in a book.
Yes.
And, so they know very much what I do. They're very proud of the fact that I'm a scientist. And I do a lot of work with women in science and encouraging people that are minoritized in academic spaces to try and, encourage people to come into science and to make the whole scientific community safer and more inclusive. And I have a lot of, women that I'm surrounded with that are scientists. And so one of my kids, I don't know, he was probably 4. And I introduced him to one of my friends that's a man. And I was like, this is my friend Adam. He's a scientist. He goes, I didn't know boys could be scientists. I thought, we've swung the pendulum a little too far in the other direction. But
well, that's a seismic change in culture, isn't it?
So one of them wants to be an engineer or a YouTuber, and the other one wants to be an astronaut.
I see.
Okay.
And you're an ambassador, aren't you, for the American Association for the Advancement of Science? Tell us about that.
Oh my gosh, it's the honor of a lifetime. I was asked to apply for this ambassadorship, and all we knew was that it was so you could be a role model for young girls. And I thought, yeah, absolutely, I'm in for that. So I applied. And I couldn't believe I was selected because they had hundreds of applicants that were, just really impressive suite of women all across the STEM disciplines. And we've done all kinds of things. We've been on TV shows. We're featured in museums. We're in textbooks. I don't know if you can see it right back there. Which way? There it is. There's a full-size statue of all of us that was 3D printed. It was showcased on the National Mall in Washington, D.C. My statue was in the Smithsonian. So that's the whole kind of action figure. But it really raised, I think, the public consciousness about the contributions that women make. And one of the reasons that Lyda Hill decided to do statues is because in the United States, if you look at the 12 largest cities, there are hundreds of statues of men, but less than 6 statues of real women.
Oh, yes.
And so if you think about what statues mean, which has been kind of an international conversation in the past 5 years or so, who we choose to immortalize in statue form speaks to what contributions we value. And women have largely been left out of the conversation. Their contributions to science have been ongoing, but they have not been given the status, they've not been given the credit that they deserve. So this was an opportunity to bring women back into that conversation and display them in a kind of a prominent way. And oh my gosh, we were all there for the opening with the statues. I cried my face off. There was a little girl that came up to me and she was like, "You're a geologist?" And she pulled all these rocks out of her pockets. And we are sitting on the ground in front of my statue and we're identifying the rocks and talking about rocks. And she goes, "I want to be a geologist just like you." And I was like, hold it together. But then, her mom's asking her questions. And I said, "Oh, what did you learn today?" Because it was all 100 statues and all the women were there with their statues. And she goes, "I learned that I'm a girl and that means I can do whatever I want to do."
Brilliant.
Oh, that's amazing. That's amazing.
So when did you decide, in your upbringing that you wanted to be a geologist. Were you like her?
Oh no, my undergraduate degree was in Shakespearean theater.
Oh,
And I moved to LA to be an
I
actress.
feel.
Yeah. So, and then I felt an earthquake, the Hector Mine earthquake. It was a magnitude 7.1 out in the desert, felt strongly across the Los Angeles area where I was living. And I went the next day to volunteer at the U.S. Geological Survey in Pasadena, Caltech. And they were like, sorry, we're busy. Don't try and do that the day after a big urban earthquake, right? So
yes.
I ended up going back about a week later, and they let me volunteer for a little while. And then they said, you're actually really good at this. And they hired me.
But what did you do? I mean, you say you volunteered. What did you do?
I was sending faxes, if that tells you anything about how long ago it was. And then I started working with a woman named Lisa Wald, planning lecture series. And then they needed somebody to go to like a school to do a talk. And I was like, I'm really good at talking to people. That's like my whole job, right? I can act like a scientist and go do that. And I did have a geology background because I had taken some geology classes in college because I really liked it. My dad is a naturalist. I really enjoy science and the natural world. And so I did have some background. And then eventually at that position, I became the outreach and education coordinator for Southern California, which has a significant amount of the earthquake risk in the United States. And after about 6 years there, I said, you know what? This is my jam. And I went back to grad school and got a master's degree and a PhD in geology. Yeah.
Wow, that's so interesting. But what strikes me about your story and about this little girl, being an educator myself, one event, just one single event, can change a person's direction of life completely.
Yeah.
And this whole thing of science communication is, I don't think we realize how important it is, because school is not about science communication. And most kids just go through school, they just go through the motions, but they don't really know anything about science, or because there's such a vast field of things to learn and I think everything sort of just glides past, and we need science communication for girls as much as for boys, well, for everybody. And to get people excited about things like the rocks under your feet and what they can tell you, and how one person that makes one comment, or like you experiencing an earthquake and saying, well, I want to do something, and it pushed your life in an entirely different direction. That's so fascinating. It's amazing.
Yeah, I feel like at school, in science class, I felt like everything had already been discovered, because at least I was going to school, it was delivered as a set of facts, and you memorized the facts, you wrote them down on the test, and you got it wrong or you got it right.
Yeah.
And so I think a lot of times in the educational systems we have currently set up, we miss the point that science is a process. It's exploration, discovery, it's dead ends and null results. And that as you get more data and information, you'll actually change your position, which is critical. And so I feel like part of what I do all the time is try and tell kids, like, look, there are so many questions. Every single question we answer breeds 3 more questions. And so we need you to come and help us answer these questions. And these answers can save people's lives. They can really make a difference. They can help us to understand the world we live in. They can help us to save our planet, so that they recognize that it's not just the answers in the back of the book, that they can be the ones to find the answers that are still out there.
Yeah, science is about detection, isn't it? It's an investigation process. It's not just an encyclopedia of what we've discovered.
Right.
But that's not the way it's taught. It's so interesting.
No, we've got to get that message across.
The only questions in science books are the ones that are meant to test children. And I think we don't tell the stories of scientists enough. Stories and telling stories reveals this thing that for every question for every answer there's 5 new questions, because once I mean, and we don't tell the stories of people, and we present it as if it's this is a body of knowledge, but it's yes, it is, because we've come so far and we stand on the shoulders of all these giants, but there are so many minor giants who are cogs in a wheel that's turning and turning and turning and turning. And you, being a grade 9er now, could be the next person that develops a machine that can perhaps detect where the next big earthquake will be and give people a couple hours warning. And we should present it like that. So
Yeah.
I think science communication is so, and telling the stories. I mean, Mary Anning, she was, nobody knew about, I didn't know anything about Mary Anning until I read Bill Bryson's book. And she was one of the first people.
We all knew the rhyme though, didn't we?
Well, yes, but we never made the connections, you know?
No.
So I'm glad your statue is there, Dr. Wendy.
So I've interviewed a lot of assorted geologists, many of them paleontologists, and one of them, this is, what's her name? Dr. Susie Maidman. She's at the Natural History Museum just up the road in London. And she was like the little girl you talked about, because she was about 4 and she had a toy dinosaur, one of these stuffed cuddly toys, you know, and she was being interviewed, as it were, by her grandfather. And he said, what do you want to do when you grow up? And she could barely speak. So she said, dinosaur.
Mm-hmm.
And it turned out to be true. She is now actually, it's not a dinosaur, it's an archaeosaur expert in the Natural History Museum in London, Kensington, you know. I expect you've been there. Oh, no, you haven't. Oh. Do come, it's worth a visit.
I'm ready to travel to all the places.
Bring the twins.
No. Transatlantic flight, we are not there yet. Not yet.
No.
Can't get them to sit still through dinner. That would not.
Sorry, John, go ahead.
When does an orogeny become, or how many earthquakes does it take to make an orogeny?
Depends on what you call an orogeny and when you think that begins. But it depends on the size of the earthquakes. Some of the earthquakes in the Himalayas, you know, there's evidence that they have moved the fault 22 meters. I mean, it's just mind-boggling how much they can grow. And so, you know, you can think of tectonic processes like a colossal battle. You know, we have these kids, I watch a lot of like Godzilla kind of movies where it's the epic battle. So it's the epic battle between erosion and weathering and tectonic uplift. And so it depends. How many earthquakes does it take? Depends on how fast your erosive processes are happening. Depends on the climate where you are. And oftentimes you have mountain ranges that grow so large they will change the atmospheric system so that it changes climate for an entire area. So
well, even here, I live in Sussex near the coast. It's 10 minutes walk to the beach. And even here we can see behind us the downs. There's the clouds on top of the downs. Everywhere else is blue sky. So yes,
you just reminded me of a question I wanted to ask. I was thinking about climate change. Do you think that climate change could have an effect on earthquakes and the movement of tectonic plates, or not really?
I don't think so. I feel like people are actively exploring that question, but earthquakes start far below the surface of the earth. And for the most part, the things that are happening with climate change right now are happening near the surface. You know, we can talk about changes in aquifers as we withdraw water that's not being replaced because you're changing the variability of where rain is falling, for instance. And so long term, is that possible? I'm not sure. Right now, I don't think that's a thing. What it can impact is there's something called ice quakes within glaciers. And so there are changes in the amounts and types of ice quakes that people are seeing as the glaciers are melting.
Okay.
Does your expertise extend to the mid-ocean ridges?
I mean, in minor ways.
Yes. This is sort of the opposite of an earthquake, isn't it? It's where it's pulling apart rather than crushing together and sliding past.
There's three different kinds of boundaries. One is a convergent boundary. That's where they're slamming together. That's where you get the large mountains and the largest earthquakes along subduction zones. You have strike slip boundaries, which are the ones that I tend to like to study, where things are sliding past each other. And then you have divergent boundaries, where new crust is being made as the crust is pulling apart. And so there are earthquakes along the mid-Atlantic ridge. They tend to be along transform faults that are adjacent to the ridge, that are helping to accommodate motion, because everything gets really complicated when you try and do it on a sphere.
Okay.
People are always confused when we show visualizations of earthquake waves, because we have all these sensors and you can actually see the waves crossing, but they're like, wait, why did this earthquake in Japan come in from this totally wacky angle? Japan's over here. And you're like, yeah, it's called a great circle path. Have you ever looked at the airplane flight? You're like, why are we going like this? Well, that's actually the shortest line distance on a sphere. So there you go, flat earthers. It's another line of evidence that we live on a sphere. If the earth was flat, cats would have pushed everything off already. So, there's two lines for you.
Aren't there some waves that go directly through?
There are. So there's many kinds of waves produced during earthquakes. Two most famous ones are called surface waves. They travel along the surface of the earth, or the Love and Rayleigh waves. There's also body waves, P waves and S waves that go through the interior of the earth. So they come up from above. Some waves go straight through the interior of the earth, but the idea of it is that we can use these waves very much like the doctor will use an ultrasound machine. So an ultrasound machine is really just putting waves into your body, and it looks at the differences in density by how the waves are reflected and refracted within your body. And so that's what we do inside the earth. You can think of the seismometers almost like pixels in a camera, or like an ultrasound spot. And then the earthquake waves come through, and we can see the differences in density and changes in temperature, the boundaries, changes in pressure, those sorts of things. By examining the path and the speed of the earthquake waves.
Can I ask a really stupid question? I was just thinking about this. So a seismometer, is it actually something that is stuck into the earth, and how deep does it go, and at what intervals, or is it something that and what's the deepest that we've been able to dig into the earth?
So those are dumb questions. There's no reason.
The MOHO.
The seismometers there are lots of different kinds of seismometers. You can actually build seismometers using Legos. There's a Lego seismometer set that will actually detect earthquakes, and you just set it on the ground. We have small sensors called Raspberry Shakes that you can buy for $400 or $500, and those, again, sit on your desk or on the ground. The seismometers that we use generally for science, the broadband seismometers, for instance, that are part of the Global Seismographic Network, we'll dig down into the ground maybe 10 or 15 feet and place them in a vault. And we do that so that we can get away from all of the things that are vibrating the near surface. So, wind, things that are walking around. So we want it to be in the quietest location that we can get it. And so burying it helps it to stay quiet, helps it to not get messed with. But I tell you, it's really interesting. Some of these seismometers, like the ones we have in Alaska, they are not lonely. You can actually see bears coming up and rubbing on the station. You can see their footsteps. There are lynxes, there are moose. There's all these things that are walking around the seismic stations. And we actually can detect that because they're so very sensitive. They can detect the motion of the ground that's as small as the width of a human hair. So these big bears like rubbing up on it.
So asking the question, did the earth move for you, may not be such a silly question.
It is not. And we can detect earthquakes, from the other side of the world. So there's a really cool app that we have. It's free. You can get it on your browser. You can get it on your phone, called Station Monitor. And using that, it's a graphical interface. You can click on any seismic station that we get data from anywhere in the world and see near real-time data coming in. So after any earthquake that's, kind of notable, 6.5 or greater, I'll actually go on and post on Twitter like, hey, look, this is what the waves look like under me right now here in Maryland, even though that earthquake was in the Philippines or wherever it happened to be. And that really blows people's minds. And I think it brings home the fact that the earth is so connected. Even if you live in Florida or somewhere that has no earthquakes. The idea that a seismometer down the street from your house could detect earthquake waves from a quake that happened on the other side of the world, it hits you in a new way, you know?
Mm. Do you know, the experts in this country recently published a map, an interactive map of the likely effect of ice melting and sea rising between now and 2050. And they're assuming that a 35 centimeter rise. And you can see how along the coast here, a lot of the land is flooded. So, for example, just down the road from me, for sale at the moment, there's an £8 million house. And in 30 years' time, it's going to be suffering annual flooding.
Yeah.
Does this have any impact on earthquakes? Because there's going to be more lubricant water getting into cracks that it didn't used to go into.
Well, but water at the surface. And so it depends on where the fault is. And again, the faults, we really see lubrication of faults as a problem in places where we're injecting water deep into the subsurface. People call it, colloquially, it's called fracking.
Yes.
But what the fracking actually creates small earthquakes. It doesn't tend to create large earthquakes. What creates the larger earthquakes is called wastewater injection, which is all of the stuff that the frackers used that they don't want anymore. So it's a slurry of wastewater that then gets injected into the deep earth, and not the deep earth like the mantle, but farther than where they're getting the hydrocarbons out. And so there are faults in that location that are in the orientation where they could experience earthquakes. They'll start to have these earthquakes at a much, much, much higher rate than they would naturally. So it's like they're using up their earthquake budget for the next million years, but they're doing it right now.
So it might be quieter afterwards when it's all happened.
Well, there's a lot of
the other thing, you mentioned waste, and of course another problem that earthquakes present for us is they might disturb the waste, like radioactive waste, that we want to remain undisturbed. So
there's
do you recommend any locations where it might be reasonably safe to store this horrible radioactive waste that's going to be radioactive for millions of years?
It would take far more than just me to make an assessment like that. You have a whole panel of experts that has to look at all sorts of things. Like, it's not just about the faults, it's also about the aquifers and what other things are nearby. So it's a whole panel of experts that would need to weigh in on the safest locations. I certainly could contribute to a very, very tiny piece of that, but it's, like Yucca Mountain, which is a waste site. There was a lot of thought that went into that, and there's some concerns, and it's a difficult problem.
So Wendy, just one last question. I really want to know, what is the deepest that we've been able to drill down Earth?
I don't remember. It's a mile or two. It's not very far.
No.
Yeah.
Because it gets too hot, and then the drilling equipment doesn't work. It gets hot really fast. So the geothermal gradient inside the Earth, it increases really rapidly. And so it's really not very possible for us to go very deep before it becomes untenable.
Yes. I can testify to that because I went down a gold mine in Ghana a few years ago, and they'd recently dug to a deeper level thanks to installing a huge refrigeration system to send cool air down there so that people could actually survive.
Is that mine deeper than the deep? I don't know, but as far as I know, the deepest one was in Joburg. The deepest mine shaft. I don't know. Maybe that one in Ghana has surpassed it. But
are you suffering from an earthquake, Tercia? You're going up and down. Are you suffering from an earthquake?
Yes. No, sorry. I'm sitting on the bed in my mom's spare bedroom. No, the deepest mine shaft was in South Africa at Gold Reef City somewhere, I think, something deep, Western Deep.
Steve's found one for us and put it in the ticker along the bottom.
I can't
7
read. I'm not
kilometers.
wearing my glasses. I'm not
Yeah.
wearing my glasses.
Kola
But,
Peninsula drilled a hole 7 kilometers, 23,000 feet deep. Thanks,
Okay.
Steve.
Thank you. That's
Yeah.
the kind of question the kids in my class will ask you. What
Yes,
is
yes.
the deepest? And will we get to the core? And well, I don't think we can get to the core. In fact,
No.
it'll be too hard. It'll just be too
Everything
hard.
will melt before we get there. Yeah.
You know, as an earthquake geologist, I study, the top 10 kilometers of the crust, and I really focus on the near surface. And so I
Yes.
feel really bad for all of these seismologists that like study the mantle. I'm like,
Yes.
wow, you guys never see. I mean, it's like there's a wall of rock between you and the thing you spend your entire life worrying about. And
Yes.
you're never going to see it. That's so sad to me.
Yep.
That is sad.
Well, I'm noticing that we've done an hour, and the show is called An Hour, and Tercia's phone is about to die.
Yes.
So I see. So what I'm going to say is thank you very much, Wendy. You've been fantastic, like I knew you would, because I chatted with you before, as you remember. And thank you, Tercia, for co-hosting. And thank you,
My
people,
pleasure.
for watching. Thank you for people for watching live, and people who watch in the future. And I'm going to see if I can find the outro. Though Steve's back, he may have found it before me, but I've made an
Bye,
outro.
Wendy. Lovely talking
Bye.
to you.
Thanks so much for having me. This was amazing. It didn't feel like an hour.
No, time flies when you're having fun.
That's true.
Yes, absolutely. Time flies. Thank you.
Bye, guys.
Say
Bye.
goodbye.
Bye, guys.